Hello everyone, in this video I will be talking a bit about the differences between modern orbital space rockets and intercontinental missiles, and how this has changed through history. Now of course to some this might already be quite obvious, and I will be talking about a few rather basic things, but I will also go a little bit more into detail and talk through the history and the physics and design behind this, and why these are so different now and used to be so similar. Now, first of all, a little heads up again. Intercontinental ballistic missiles are again a subject that is somewhat politically and morally touchy subject, and I am generally morally not a big fan of building technology with the sole purpose of killing people, but unfortunately long-range missiles are an integral part of the history of rocket science and are still a relatively closely related technology to space rockets, and examining the designs is still scientifically and technologically interesting. I will use weapons technology mentioned in this video purely as an example and to examine the technology and design behind it, independent of political motivations or questions, and I will use judging words like a good design or things you want to do when designing a missile from a purely technological sense from the point of view of the designer, independent of what the missile might later be used for. Now to start, let's go back in history a little bit to the beginning of the space race and the early days of rocket technology. Now the beginnings of rocket technology are here a slightly vague term because in a way more simplified form, rockets have been used for a very, very long time. So long that it's more a question for a historian than for an engineer. But basically simple black powder fireworks rockets have been used for centuries for different purposes, for fireworks, for message delivery, and also for military purposes. But what I mean with early rocket technology is the beginning of slightly more sophisticated rockets, liquid-fueled rockets, rockets with enough performance that they have theoretically the technology that they could be modified into space rockets, or they hold the technology that could be used to build space rockets. So I'm talking about post-World War II, early Cold War technology. And when we notice that these early space rockets are very similar to missiles at the time, then there are two reasons for that. One very obvious design detail related reason is of course that they are directly related. In those times, space programs were basically spin-offs of missile programs, and the earliest space rockets were literally slightly modified missiles. And shortly after this, when these technologies started to diverge, the engineers in both missile technology and rocket technology both still kind of stuck to what they knew. While it was a rather innovative time, they didn't want to unnecessarily reinvent the wheel, and so the overall design layout of their rockets stayed similar to what they had done before, back when space rockets and missiles were literally modified versions of each other. And so even when designated space rockets and missiles were built as completely different vehicles, their design still had a lot of properties reminiscent of each other. Then there is also a more sophisticated physical reason as to why these make sense to be related technologies, and why they made sense to be so similar at the time. That is, back in those early space race times, obviously, since it were the times when the first objects were sent into space, this was basically the limit of what technology could do. Back then, space meant very low Earth orbit, and reaching a very low Earth orbit and reaching a suborbital trajectory that reaches halfway around the Earth onto another continent does require very similar amounts of delta V. The suborbital flight requires a little bit less delta V, but it's not like the difference between orbital rockets and suborbital rockets that we have today, where suborbital rockets just go vertically up and peak just above the 100-kilometer line and go back down, whereas orbital rockets usually go to geostationary orbit or further out. Instead, the ballistic missiles that went on suborbital trajectories needed a lot more delta V than just a suborbital flight, because they still needed to cover that range. They actually had to get pretty close to an orbit, not quite to an orbit, but pretty close to an orbit, just to cover that range in a ballistic trajectory. while the orbital rockets, of course, in the earliest day didn't really afford to go to geostationary orbit for no actual reason or to go on an escape trajectory. Instead, they stuck to a very low Earth orbit, and so the delta V requirements and flight profile requirements were very similar back then. The rocket engine technology and fuel tank technology and fuel mixtures back then just so made it possible to send something into low Earth orbit or to send something on an intercontinental trajectory, and so both missiles and space rockets had to be designed to use the best available technology with the maximum possible effectivity, with the best possible performance, just to be capable of fulfilling their purpose in the first place. They really couldn't afford any further fancy design details that would allow them to out-strategize other missiles or to reach deeper into space, and so rockets back then were purely performance optimized. And that is where these technologies started to diverge. With more modern rocket technology we got better performance, and now rockets no longer have to be purely performance optimized. They still have to be very performance optimized. They still have to be incredibly lightweight. They still can't afford the same factor of safety or margin of safety that is usually used in airplanes or cars, but they can now afford some optimizations other than purely optimizing for delta V. Now, space rockets did change a lot, but they probably stayed closer to that initial optimization than missiles, because they are still somewhat performance or delta V optimized, since they go further and they don't need many other optimizations. So that is one of the first design differences or purpose and optimization differences between missiles and space rockets, is that today space rockets need a lot more range. They no longer just go to low Earth orbit, and while some very early deep space missions were launched on low Earth orbit rockets with an additional little upper stage or interplanetary stage, space programs started to design space rockets that could reach higher orbits than low Earth orbit pretty early, and then of course the Saturn V, for example, could directly push a payload to escape trajectory without an additional upper stage. Meanwhile, missiles went through a whole lot of other changes that are really advantageous to missiles but don't really do anything useful for a space rocket. For once, modern missiles are, for example, designed to be storable and easy to launch. That's not very useful for a space rocket because space missions are usually planned a long time ahead, satellites are designed over years, and you have the time to spend days preparing your rocket for launch, and you can afford the infrastructure. So they can keep using the most efficient fuels and the most lightweight and high-performance technology to extend their range, specifically cryogenic fuels, which need to be prepared and need to be fueled just before launch, so you need a lot of fuel loading time and preparation. Meanwhile, missiles are ideally designed to be mass manufactured, then stored away under possibly less than ideal conditions for a very long time, and ideally with not too much maintenance or care, and then be able to be launched on a moment's notice with no preparation and a very small team of basic military personnel. After all, a main point of nuclear missile strategy is deterrence, so whether you actually use them or not, their ability to retaliate is a key design point. A missile that cannot be launched in the time window between you noticing your enemy launching their missiles and those missiles striking you is basically useless as a defensive. The whole point is that you are capable of sensing the enemy launching their missiles and then launching your missiles in retaliation before being wiped out. You demonstrate that you are capable of that, and knowing this, your enemy will hopefully not strike for fear of retaliation. That is the whole point of deterrence. And depending on how good you are at sensing the enemy's missiles, how far away they are, how they are designed, and how well organized you are, that means you have some 10 minutes or so to get your missiles ready to launch. So they ideally have to be designed to be stored fueled and be able to launch right from their storage. So cryogenic fuels are basically not a possibility. Missiles also have very different burn and maneuvering phases, which started out very similar in the beginning, of course, with both just starting vertical, then slowly pitching over in a gravity turn, and basically reaching the closest thing to an orbit they could. But nowadays that has changed a lot. Nowadays, space rockets need to be capable of doing orbital maneuvers long after launching. They have to go through a coast phase and then potentially after an hour reignite their engines to boost up their orbit, then go into geostationary transfer orbit, then a few hours later do another burn to circularize their geostationary orbit, and then perhaps another few hours later do another very small, very precise correction burn to adjust their inclination and reach the target orbit, whereas missiles have a relatively simple flight profile. They have one mission: they have to hit a location on Earth, which doesn't really require many burns or many correction burns. The orbital mechanics here is relatively simple. You go upwards until you leave maybe the very densest part of the atmosphere, then you turn over into the direction of your target, and you burn basically until your projected impact point is on target, and then you shut down your engine. You may not even need any corrections or even a lot of precision in that first burn, as you can potentially use aerodynamics during re-entry for your final adjustments. This means that missiles generally need much less sophisticated, less high-performance technology. They don't need reliable engines, and they can of course basically invest that leftover potential into other optimizations. One key part of those being stealth. Stealth would be absolutely useless for a certified civilian satellite launch. In fact, it's even the opposite. Satellites are required to be trackable, so if you build a very small satellite, not necessarily because you want it to be stealthy, maybe just because you want to build the cheapest possible satellite, so it's basically a flying smartphone with a camera and a radio receiver, you might not be allowed to launch that because it's too small and it can't be tracked, so it's basically dangerous space debris that no one actually knows where exactly it is. That's very dangerous, and so in this case you have to add something like a big reflective mirror or a radar beacon to make your satellite well visible and trackable, whereas missiles of course are the exact opposite. As we come back to a deterrence strategy, it's in fact very useful if your missiles are hard to notice. And with more modern technology, it's even possible to counter or intercept missiles. And it's pretty hard for a missile to be armored or defended against this kind of interception by what's basically anti-missile missiles, and so if your potential enemies have the missile technology to build these anti-missile defend missiles, which in defense and deterrence strategy by definition they have, a missile without stealth becomes pretty pointless. And there's many things you can do to make your missile less notable. Now, one very interesting thing that you see in modern missile designs is an extreme thrust-to-weight ratio that seems insane to space rocket designers, because it's not necessarily efficient delta V-wise or performance-wise. It's not necessarily the most lightweight design you can go for. But what it does is that it allows the missile to do its entire burn from ground to its intercontinental trajectory in a very short time. Often they stop their engines before even leaving the atmosphere, and they don't have to run their engines outside the atmosphere. After all, they don't need to circularize their orbit. They're not going to an orbit, they're going to a very wide suborbital trajectory. So they can actually shut down their engines still in the atmosphere and then on a pre-calculated trajectory leave the atmosphere and powerlessly just drift on their ballistic trajectory to their target. That means if you have a high thrust-to-weight ratio, you can keep your burn time very short, which makes it much harder to notice that burn by infrared satellites or other remote sensing technologies. And you can also keep that burn completely close to you and within the atmosphere, which makes it much harder to notice. And if you have to stage to reach your delta V, then you can do that staging at a very low altitude, which means that the biggest part of your rocket, and thus most visible part of your rocket, just stays at home, and only the very small upper stage actually leaves the atmosphere and can be seen. Apart from this huge engine and structural difference, the main difference between missiles and space rockets is probably the fuel choice. Again, space rockets don't need stealth, and apart from a few other points like fuel tank weight, they mostly go for the most efficient fuels they can. But it's actually pretty much a physical or mathematical law that the more efficient a fuel gets, the less stealthy it will be. Now, there are a few other chemical or design factors that also have an impact on this, but it's still a very strong correlation. For one's specific impulse basically means energy per mass. So high specific impulse fuels tend to be those that burn very, very hot. And hot burning, of course, means that it's easy to sense with thermal imaging or infrared satellites. And on the other hand, high specific impulse also means a lot of power per thrust. If you remember basic high school physics, power equals force times speed, and specific impulse, which basically is the measure for efficiency in a rocket engine, even though it's technically not efficiency, but that's basically semantics. It is what we use to signify how efficient a rocket fuel is. That specific impulse is basically the speed at which the exhaust leaves the engine. So high specific impulse means high speed, and speed times force equals power, so high specific impulse means more power for the same thrust. Power that again translates to heat, which can be sensed by satellites, vibration and noise, which can be sensed seismically, and a very bright and loud object to be seen by anyone who is just happening to be nearby. Of course, a lower specific impulse also means you need more fuel, a bigger, heavier rocket, and thus more thrust again, but actually at the delta V range that you're in with an intercontinental missile, you can at least somewhat lower your specific impulse and still have a net reduction in engine power output, before the exponential part of the rocket equation just goes haywire and you end up building a absolutely gigantic rocket. Of course, an engine with a specific impulse of 100 seconds isn't really good for anyone. Still, rockets are not stealthy. It's not about making your missile impossible to sense. It's about making it so hard to sense that it's too late for defense, or that one of your 200 missiles actually comes through. In fact, that's an often missed point by conspiracy theorists. Rockets are hard to miss. If you have something similar to a Saturn V and you launch it, then everyone around the world with half-decent measuring equipment will know. Now, you could of course go a lot more into detail about this, but this is already getting quite long, and I hope this at least showed the basics of why maybe today classifying modern space rockets as a weapon technology is somewhat outdated paperwork. If you repurpose the technology used in any modern orbital rocket to build a missile, that missile will be shredded by missile defense before it has any chance of ever reaching its target. And it would be useless on the defense, as it would take days to prepare for launch. Meanwhile, using the technology used in a modern missile to build a space rocket would give you something pretty useless too, as they intentionally keep their fuels simple and their specific impulse low, so reaching geostationary orbit with that type of fuel would require an absolutely gigantic rocket for a tiny payload, if the engines even relight to circularize your geostationary orbit. So that's it for this video. In my next explanation I will probably do some updates on the current situation of SpaceX and the BFR and ITS program, as that is actually getting pretty exciting right now. And after that I might be talking about hypothetical strategies for defending against large asteroids, or analyzing a few misconceptions about space elevators and why they probably won't be as useful as some people might think. I hope you found this somewhat interesting, and as always, thanks for watching.